Hi, everybody. Welcome to this last session for Physics 101. Today, we're going to deal with one part of actually nuclear physics. We're going to get into the so-called weak nuclear force, which is responsible for the radioactivity. And we're going to explain it basically in a historical context and how it was discovered. So we're going to start with the radioactivity as a phenomenon by itself and the different types of radiation and so on and so forth. So that's actually what the chapter 25 is all about. Don't forget today we have the last lab also. It's going to be on campus, so we're going to be physically there. And we're going to go through the universe per the perception of Mr. Einstein. So basically the general theory of relativity, which is a topic that is part of this class too. So we're going to go through the ideas that were covered there, and we're going to explore them, and we're going to get some interesting conclusions about how the universe is really actually is, which diverges away from our perception up to this point, basically on Newtonian mechanics. The fact that we use the basic ideas from mechanics, which are the 3 laws of Newton, and based on that, we described how the universe would look like, and namely how a reality would look like, namely forces and accelerations and velocities and all of that. The fact that these things do not apply, or at least they come short of explaining the big picture in terms of the universe, led Mr. Einstein to the new theory, which we're going to explore in the lab. So this is basically what's going on. So let me delve into the topic of today, which is chapter 25, which is actually part of the exam also that you guys are required to prepare for. Exam 4, I should say. Exam 3 is this week, and then the final, which is considered exam 4, which is next week. So please follow, make sure you do the preparations, otherwise you're going to miss some two things. You're going to miss the grades, which are actually a nice thing to have, because the minute that you do your review, you're going to get full credit for it. Furthermore, the review actually helps you prepare for the exam. There is no review for the final exam. The final exam is comprehensive, so that you guys know. So let me share with you the screen. So this is basically the topic is chapter 25, and we're going to be discussing basically radioactivity, and just to put it in perspective of what we know today, okay? There are 4 forces in nature. There is the force of gravity, which is, if you guys remember, it's really, at least from our vantage points up to this point, is based on Newton's law of gravitation, which gives me the force as it's really a vector, so I'm going to just take its magnitude. The product of 2 masses, so 2 masses near one another, they will pull on each other. This is mass m1, this is mass m2, and the distance between them is r. So the product of these 2 masses in kilogram divided by the distance squared between them times g. G happened to be a constant of nature, which is 6.67 times 10 to the negative 11, of course, in the proper units, which is Newton per kilogram squared times meter squared. So this is basically the force of gravity. And this is a kind of an easy one to relate to, because of the fact that this is based on our daily experience. The reason why we get tired, to begin with, honestly, is because we're fighting gravity all the time, moving up and down, left and right, and so on and so forth, carrying stuff and things like that. The second force that we actually discovered also is the force of electrostatic force. I mean, it's electromagnetism, to be honest with you. There are a bunch of laws that governs it. We just barely touched the surface of it. Force of electromagnetism. So in a bare minimum, so this is not the whole picture. So this is just a bare minimum. Is the electrostatic force that governs 2 charges, namely if I bring charge 1 in here, Q1, and charge 2, Q2, and the distance separation between them is also R. This force is proportional. So there is a constant in here depending on the medium, where they are. If they are in the air, that constant has a value. If they are not in the air, for example, inside the water or somewhere else in different medium, that KE changes, okay? Or if there is a medium between them, so one of them is in the air, the other one is in the air, but there is a medium, for example, that has specific properties, then that constant changes really. So it's not always constant, unlike this constant, which is really a fundamental constant of nature. So it's the product of the two charges divided by, again, the distance squared. Now, this force may or may not be positive. In a sense, it could be attractive or repulsive. And like this one, which is always attractive, masses always attract one another, okay? So this is actually the second force in nature. There are two other forces that govern nature also. One of them is kind of hard. Both of them are actually honestly hard to understand, but I'm going to list them in here. There is the nuclear forces, and there are two of them, different ones. They are not related, actually. As a matter of fact, the weak nuclear force is more related to the electromagnetism than the nuclear force, the strong one, nuclear force. And this is the one that is responsible for radioactivity. Okay. The mechanics for it, the mechanism for it is a little bit outside of the scope of this course, but I'm just mentioning it in here because it's a good idea to have a list of them in here. Finally, the strong nuclear force. This manifests itself in two places. First of all, in holding the nucleus together. The nucleus is made up of two particles, really. So the nucleus has two main particles in it. So either a proton, I'm just trying to highlight its color as being dark color in here, or a neutron, okay? So you have protons and neutrons. This force is also attractive, okay? This force attracts between the protons and protons and protons and neutrons, and neutrons and neutrons. So this is kind of a force that glues the entire nucleus together. Because if it were not for it, protons are positively charged. So if it were up to electromagnetism, these charges, they will repel each other, and the nucleus will not be stable. However, this force is stronger than electromagnetism and helps glue together the nucleus and keep it from falling apart. So this is important. So that's when it manifests itself in part here, and it manifests itself in holding the nucleons themselves together. What I mean by that is nucleons are actually protons and neutrons. That's just a common word for both of them because they make up the nucleus. So they are particles of the nucleus. Whenever you see an ON at the end, that's a particle. So these are particles of the nucleus, which are really a fancy word of saying protons and neutrons. They're trying to clump them together. So if you look at the proton inside of it, there are three tiny particles in here, extremely small. And those three particles are quarks. And for the case of a proton, it's made up of two quarks. It has two types of quarks, we should say, three quarks, but two types. So you have an up quark and another up quark and a down quark. So up and down doesn't mean much. Okay, don't think of it like one of them is sending up, the other one is saying, no. It's just a way of trying to distinguish things. Just when we call things positive and negative, it doesn't mean that when you have a positive charge is like a better thing than having a negative charge. So it's just names, that's all, trying to distinguish things, okay? And for the case of, so this is a proton. And also for a neutron, it's the same thing. It's made up of three quarks also, with the distinction that the quarks are actually an up quark and two down quarks, that's all. Okay. Now, what holds this thing together is actually this same force, the strong nuclear force. It glues these particles together, okay, to form the inside of them. So those are, in a nutshell, the strong nuclear force, which is really way outside of the scope, trying to get into the details of it and understand. And there is a theory called that has to do with colors, actually. Not the colors that we know them, but just basically they gave it a name for colors because it comes in 3 different flavors that you can clearly see, and similar to red, green, and blue, and how they interact to form the different colors. Same thing in here. There is a distinction between the three quarks that interact in a similar fashion, just like when positive and positive attract, or negative and negative, positive and positive repel, or negative and negative repel, or positive and negative attract. There is actually similar behavior in here, except you have 3 elements to it. So they gave it the word color for it, not in a sense that the color that we see with our own eyes. Anyway, so the topic of today, since we covered this one, so I'm going to put a check mark on it in detail. We covered this one to some extent, not really honestly in detail. We saw it in this format, which is just basically we scratched the surface of it, at least in this class. There are other kinds of forces I mean, most of the forces that we deal with, at least in chemistry, are related to electromagnetic forces. Basically how electrons are moved from one compound and put in another compound. So all of chemistry really deals with this kind of force, okay? When you have a fire somewhere, that's actually a chemical reaction, and all there is in there is just rearrangement of the electrons, that's all. So the fact that we use actually electrons to see, to hear, for all of our daily experience, the reason why I am sitting and not actually going through the chair, not penetrating through the earth, all of us actually standing, is because of these interactions that we're talking about in here. The electrons mainly. So it's really, this is a topic that friction also can be included there. So a lot of these things that we express them in different words on a daily basis, they can relate to this one. Force of gravity is actually alone by itself, which is weights and how masses basically pull on each other. And that's the force that is helps put the entire solar system together, and actually the entire galaxy together. And that's the lab today, actually, because of the shortcomings of this theory that we discovered actually up to this point. Mr. Einstein came up with a different interpretation that explains that better than this approach that we did, okay? This one we're not going to be covering, at least now. Or actually, a part of it in the lab, we're going to be talking today in the lab about this relationship, E equals to mc squared. That is actually coming directly from Mr. Einstein's work. And that relationship can also be useful in here, trying to explain, for example, how come some nuclei are more stable than others, okay? In terms of how much energy is needed to hold the entire nucleus together. And you will see there, I mean, we're not going to get to the details of it, but the idea is that, for example, if you take the hydrogen atom, which has only 1 proton in it, versus if you take helium atom, which has 2 protons and 2 neutrons, if you add the mass of a single proton twice and a single neutron twice, you will see that the mass together of the individual particles, namely a proton plus a proton plus a neutron plus a neutron, to form the nucleus of the helium, you will see that these numbers, they will add up slightly higher than the mass of the helium, and the difference is exactly the energy needed to form that nucleus. The difference, if you multiply that difference by c squared, you will find that it's exactly the energy needed to form that nucleus. And you can go through the entire periodic table and you see the same thing, okay? So all of the elements exhibit this kind of behavior. So it's actually important in a sense that the 2 sciences are merging to one another, namely the theory of relativity that Mr. Einstein has developed, and this theory in here, which is also a robust theory, and it's probably one of the strongest things that mankind has invented in terms of knowledge. The weak nuclear force, and I'm purposely left it in here as last because we're going to be talking about it today extensively. In terms of strength, this one is the strongest force. 137 times stronger than this one. So in terms of force, I'm going to rank them from A to A, B, C, D. So this is A, the strongest one. So this takes by far. That's why it's called strong force, actually, because I mean, a strong force is weak, differentiated from another nuclear force that appears also inside the nucleus, which is the weak nuclear force. So this is the strongest. The second strength one is actually the electromagnetic force, which is a very strong force, relatively speaking, and it dominates. And there was a question actually when we did this is, if this is so strong, how come basically why it's not responsible, for example, for holding the solar system together? Why is the super weak one is the one that is? It's because matter is most of the time neutral. Not most of the time, all the time is neutral, except in extreme conditions, for example, inside a fire, where you have ions basically floating by themselves, but then charges are not too far. I mean, electrons are not too far, so they form immediately and they become smoke. And even if they are ionized, they are not completely ionized, so their electrons are still there. So nature for most of the time is there, unless you go to a discharge, for example, you form charge, and even then it's going to recombine. Even inside the sun, the total charge is zero because of the fact that you have the same number of positive charges, the same number of negative charges. So nature presented this ones in pairs so that they cancel, at least on the large scale, okay? Then the third strong force is this one, C. The weak nuclear force is the third force in terms of the strength. And the weakest force by a huge factor that is completely ridiculously small is this one, okay? So these are the forces of nature, how they present themselves. Strong nuclear force is the strongest. Electromagnetism, which is Coulomb's law that we saw actually, is the second. The weak nuclear force we're going to be talking about today is the third and the last one in terms of strength by far, extremely weak compared to the other three, is the force of gravity. So that's how nature basically presents all the forces there is to know in nature. Okay. The topic of today, again, historically, people have noted that there are elements that spontaneously, not being exaggerating on their own, okay, naturally, if you wish, emit radiation. Radiation was classified into three kinds, okay? Alpha radiation, or radioactivity, beta radioactivity, and gamma radioactivity. So you're telling me how did they distinguish between these three? Okay, here it is. You take a particle that emits radiation on its own. Here is a lump of mass, okay? And you run it through magnetic field, for example. So you have a magnet, you have a north pole in here, and you have a south pole in here. Obviously, these particles are come with a velocity v. And remember, if let's say this is the north pole and that's the south pole, that's the direction of the magnetic field. It always wants from north to south. So the particles are moving this way. The magnetic field is down, so they will be bending towards me if they are positive charged. So the alpha particles will try to come out of the screen. So alpha particles are coming out towards me. So whenever I see particles that if I put them in a magnetic field in this direction and the particles are moving this way, I know that they are positively charged. So this has a positive charge. Furthermore, I can see the bending, how much bending it is. And I can find the ratio of charge over mass. Not only that, I know how much charge compared to that of an electron. So it turns out the alpha particles are positively charged and their charge is twice that of the electron. So their Q is 3.2 times 10 to the negative 19 Coulomb. Okay. Furthermore, their mass is 4 times that of hydrogen. course, at that time, we didn't know about helium. Honestly, when it was discovered, helium was actually seen as part of a gas that forms the sun. That's where the name Helios is coming from. Helium is coming from the sun Helios. And that they thought it's a gas on the sun until later on it was discovered actually part of the it also exists on Earth. So this is actually the nucleus of helium. In other words, helium stripped from it 2 electrons. That's it. So they will travel for a short while, but they will meet ultimately their electrons and they will disappear. Or they will interact with matter and they disappear. So they have a short range. They don't penetrate too much, okay, because of these properties, okay? So this is one type. Another type that go into the screen, beta, goes into the screen, not coming out, going in. So those must be, in this case, in this experiment, negatively charged. The reason why, again, their velocity is this way, the magnetic field is pointing this way. Had they been positive, they would have come out of the screen. Did I put it backward? I did. Okay, so they are moving this way. No. Again, the right-hand rule. Because the screen, I'm looking at it, so I hope you guys may get the point, okay? You have to use the right-hand rule, okay? And I used it wrong in the first time. So the velocity is this way. The magnetic field is this way. So if I do the right-hand rule again, the velocity is this way, the magnetic field is this way. So it's actually, I pointed my hand in the opposite direction. So if I follow the same thing as the screen is, basically it's going to go into the screen. So the first one is into the screen. I mean, the bottom line is, what is my pen? So this is the one that is into the screen. This is the one that is out of the screen. The whole thing is, if you know the direction of the magnetic field, and if you know which way the particles are coming from, if you put them in one side, then you know basically on exactly how much, which direction the positives will go and the negative will go. All you have to do is arm yourself with the right-hand rule. That's all. This is V, this is B. This is where the direction of the bending need to go had they been positive. If they bend in the opposite direction, they are negative. That's all. Don't confuse yourself and use the right-hand rule or flip it the way that I did in there, okay? So use your right-hand rule, whichever way they are going, okay? This is where the charges are going. This is where the magnetic field is pointing. This is where they will bend had they been positive. If you find them bending, if they find them hitting the other screen, not the one that you have it in here, but you have a different screen on the other side, you know then that they're actually the opposite side. And that's exactly what's going on with the beta particles, that they are negative charges, and their charge in magnitude is equal to E exactly 1.6 times 10 to the negative 19 Coulomb. Furthermore, their mass is equal to that of the electron, which is 9.11 times 10 to the negative 31 kilogram. So for all of practical purposes, this is nothing but electrons, and they are electrons. So the beta particles are electrons. There are 2 types of beta particles, though. There are 2 types of beta particles, though. Those that come with a positive 1.6 times 10 to the negative 19, and these are weird, honestly. And the regular ones, those that come with a negative charge. So these are actually real electrons. These are anti-electrons. Because a regular electron must have a charge that is negative. These ones, they come up with a positive charge. That's how radioactivity works for you. It's either one, depending on what happened inside the nucleus, that's all. They gave them a name. This anti-electrons, they gave them a name. So if you hear or read about positrons, that's exactly what we mean by them. They are actually electrons, except they don't have a negative charge like a normal electron does. They have a positive charge. their penetration is a little longer than that of the alpha particles because of their low mass. Remember, this is a big mass. This is 4 times 1.67 times 10 to the negative 27. So this is, what is 1.67 times 4? Let me try to pull the calculator quickly here. Calculator. I don't have a shortcut for it, so I'm going to search for it. So 1.67 times 4, 6.68, 6.7. I'm gonna, let's make 6.68. Okay, so their mass is, for the alpha particles, that is, the mass is 6.68 times 10 to the negative 27. Obviously, 10 to the negative 27 is about 1,000 or at least 10,000 times bigger than this one's, okay? So alpha particles are 10,000 times more massive than beta particles. The Greek letters alpha and beta, that's what they were adapted for them. So if you see alpha and beta, that's how they are adapted, alpha, beta, the beta particles. Okay, so they have far more because they're super light, so they can go very far. With the exception positrons in here, they're short-lived because of the fact that they will meet ultimately an electron somewhere and they will cancel. So a positron, which is usually it has a symbol E+, just to distinguish it from a regular electron. So if it meets an electron, in this case, energy is formed. And the symbol for energy is gamma. So this is the photons that are going to come out. 2 of them. And the reason why you have to have 2 is because the conservation of the momentum. Remember, momentum is conserved quantity. That's one of the stuff that we learned way back in chapter 4 or 5 or something, long time ago. So that's why you have to have 2 of them. One of them will not do, because it's not possible to have that. So that's something that, but the energy in here is exactly equal to, how much is the energy? Well, it's very simple. 2 times 9.11 times 10 to the negative 31 times c squared. The c squared is, remember, 3 times 3, that's 9. 10 to the power 8 squared, that's 10 to the power 16. So that's how much energy is going to come out. So if you're wondering how much how much energy is coming, it's this same number. Basically, what I used in here, the mass that have converted, this is one mass, this is the same mass, and it's both of them the same mass, which is 9.11 times 10 to the negative 31 kilogram, because they are electrons, but 2 of them, because they have one positron and 1 electron, and I multiplied it by c squared. This is one of the things that we're going to be discussing today in lab. So that's basically how much mass, how much energy is going to come out of this, if in case they annihilate. This process is called an annihilation. So this is one thing that is actually part of nuclear physics, more the old one than the one that we're discussing today. But the point being in here is this is the second type of particle. Now, the third one, each time I will have to change the material here, by the way, because if a material emits alpha, it doesn't mean that it's going to emit beta or gamma. The third type is the one that does not deflect one way or the other. It goes straight through. That means its charge is 0. So the third type is going to go straight through with no bending whatsoever. Let me change the color for it and make it in blue, for example. So the last one just comes straight through. It doesn't come into the out of the screen, doesn't go into the screen. It just comes straight through. It doesn't, the magnetic field does not impact it. So if the magnetic field does not impact it, the whole reason why I did B cross B is because I have to multiply that by, I have to use the right-hand rule and multiply the product of the charge times the product of the velocity times the magnetic field to find this force. If you guys remember, the force due to magnetic field is given by the charge times the velocity times the magnetic field. And if the radiation has a velocity, which is true, if the radiation has a magnetic field, which is inside a magnetic field, and that's true. But if the charge is 0, these things, they don't bend up or down, they go straight through. because there is no force in here. So the last type has no charge, and therefore they're called actually the gamma radiation. So the gamma radiation. For one thing, its Q is 0. There is no charge. And for all practical purposes, it doesn't have a mass either. So those are actually radiation, pure radiation. As a matter of fact, they turn out to be, before the discovery of the X-rays, they were kind of a puzzle at that point, this high energy radiation that is, because it doesn't have any mass, so it doesn't have any charge, so it can penetrate far more than the others. So it's actually electromagnetic radiation. It's part of electricity and magnetism. So this is radiation. So what's going on inside the nucleus? Nuclei, doesn't matter how big they are. Usually when they are big, they're subject more to radioactivity. Most of the elements in the periodic table and their so-called isotopes, which we're going to define exactly right now, are unstable. So what is an isotope? An isotope is the same chemical element except it has extra or is short in neutrons inside its nucleus. Let me explain. Let me give an example, like carbon 13 and carbon 14 and carbon 12, okay? Carbon has 3 isotopes, okay? Those are the 3 isotopes, at least these are some of the main isotopes. The main one that exists in nature is carbon 12. What carbon 12 is made up of is 6 protons inside the nucleus. So we're talking about the nucleus. We're not talking about anywhere else, okay? Of course, this can only exist inside the nucleus. And 6 neutrons. For a total of 12 nucleons. So remember, a nucleon is proton and neutron. Carbon 13, on the other hand, still has 6 protons. As a matter of fact, they all have 6 protons. It's where they differ in is in the number of neutrons. In here, it has 7 neutrons. And in here, it has 8 neutrons. For a total in here of 13 nucleons. And for a total in here of 14 nucleons. So the number that you see in here is indicative of how many nucleons you have. From there, you can deduce everything because the letter C in this case stands for how many protons you have, period. Nitrogen, on the other hand, nitrogen, the normal nitrogen is 14. That is 7 protons. So how do I know it's 7? It's because it's nitrogen. Nitrogen must have 7 protons, no matter what. And in this case, I deduct 7 from 14, so I'll end up with 7 neutrons. So this is the common isotope of nitrogen. Nitrogen has 14 nucleons. Oxygen, normal oxygen has 16 nucleons, okay? But oxygen, because it's an oxygen, must have 8 protons. So 16 deduct from it 8, you're gonna find 8 neutrons. The algebra is kind of straightforward in here for a total of 16 nucleons. If you look at another isotope, for example, of oxygen, oxygen 15, or nitrogen 15. So in this case, oxygen 15 weighs the same thing as nitrogen 15, but they are two different isotopes of the same elements. I mean, chemically speaking, nitrogen 15 is the same as nitrogen 14. They have, for the most part, the same properties. At least chemical properties, they are the same. Because in a neutral nitrogen 15, it has 7 electrons to compensate for the 7 protons. In the normal oxygen 15 has 8 protons, and so is this one. So this one also has 8 protons. Okay, so this is an isotope of oxygen, and this is an isotope of nitrogen. In terms of mass, they have the same mass. They weigh the same. This too, they say they weigh the same. Although chemically, they are not related whatsoever. One of them is nitrogen, the other one is oxygen, because the number of electrons is 7 to compensate the 7 protons, and the number of electrons in here is 8 to compensate for the 8 protons. However, in here, I must have 8 neutrons, because 15 deducted from 7 is 8, for a total of 15 nucleons. This one is also an isotope in here, but I have to add 7 neutrons to form, again, 15 nucleons. Nucleons, they have roughly the same, protons and neutrons, they have roughly the same mass of 1.67 times 10 to the negative 27 kilogram, making them, in this case, that number times 15, and in this case, that number times 15. In terms of mass, they are similar, but in terms of chemistry, they are completely different. So in this case, I have different orbital configuration for this nitrogen than this oxygen. And this nitrogen is similar to this nitrogen, with the exception of, because of the added mass in here, the volume is slightly different, which impacts a little bit the orbital distribution of this nitrogen versus that nitrogen. That's all. Okay, the more mass you put together, actually the smaller the nucleus becomes. So that's one of the properties because then you will have more attraction inside. Now, isotopes, they are not, as I was saying, all stable. They are for the most part unstable. Most part. What I mean by most part is the vast majority of the periodic table elements in nature, they're unstable. There are about more than 2,500 of them. Because if you start counting the periodic table, it's only about 90 something elements. But then when you include the isotopes, they are going to have a huge number of them. So this stability can interpret itself in one of 3 ways. Either an element loses an alpha particle. So imagine I have a bunch of protons in here, and spontaneously I will get 2 protons and 2 neutrons out. So it'll be short in here, in the daughter element in here, by this particle. So in here, it was an atomic number, and this number drops by 2 because I lose 2 in here. So in this case, it's the same atomic number minus 2. And because I took them in here for the alpha particle. So this is the case of the alpha particle. So if I look at the periodic table in here, and I'm missing my periodic table. If you guys remember, you have hydrogen, you have helium, you have lithium, beryllium, boron, carbon, nitrogen, oxygen, and so on and so forth of the rest of the element periodic table. So imagine, and I'm not saying that this is possible because it determines on the properties in here, oxygen loses 2 numbers from here, from 8. It must have 8 all the time. If it loses 2 protons, it's going to drop to 6, which is carbon. So it's going to move to the left in the periodic table. So every time there is an alpha emission, you have to move to the left by 2 elements. You have to skip 1 element to the next one, basically. So every time there is an emission in alpha particle, it moves to the left twice. The mass also drops and the element becomes more stable. So now you have moved from a completely one element to a different element naturally. Obviously, people were interested in this process, trying to make gold out of other things, and that's how the word chemistry coming from, which is from the Arabic word. Forgot exactly what the word is, which was actually from a Greek version of it before. So it's just trying to see if you can make gold out of other elements. So, but that's from chemistry. This is not a chemical process; it's a nuclear process. You can do it actually, if you have the right means for it. Obviously, it costs more nowadays to make gold out of other elements, but that's the point of it in here, okay? So it's feasible. But this is, you have to change the nature of the element from completely one element, which was oxygen, now to a carbon in this example. I'm not saying this is a process, but that's how it is. It could be. Okay, now, the beta particle, beta emission. If I take the same element in here or a different element that is capable of doing a beta emission, and I'm trying to draw all of the nucleons together in here, granted some of them are protons, some of them are neutrons. Okay, again, two types of emissions. Either by emitting there are three processes, I'm sorry, okay? I forgot to mention another one, okay? Either you emit a positron or you emit an electron, a regular electron. If you emit a positron, you move to the left also still by one jump. Okay, so what's going on inside? Inside the nucleus, this is the same nucleus, okay? One of the protons decides to become a neutron plus a positron. So this was positively charged. So the charge is carried by the electron, but this electron happened to be positive, that's all. This process happened in the sun, actually. It happened in all the stars. And it happens also naturally on Earth too. I think so. Okay, not 100%, but I think so. But it happens for sure in the sun. This is the one that responsible for the fusion in the sun, the one that provides all the energy for the stars that makes them go. Okay? So this is a natural process. It happens on its own. Okay? Proton decays into a neutron, which is neutral, by the way. And in this case, since it lost one proton, it also moves to the left. So this is case one. Case two, it's the opposite. A normal neutron that has no charge decays into a positively charged proton and a regular electron. So in this case, the total charge before is zero, the charge after is zero, so everything is conserved, the mass is conserved, everything is conserved. There is actually some other things also going on in here. So there is an antineutrino in here, and there is a regular neutrino in here, and there is an antineutrino in here. So this accounts for other properties that we're not going to be mentioning in here. But the fact is that this is how we know actually that this process happened, because we detected this process. This particle is actually coming from the sun. So that's how we know that this is what's going on. We detected neutrinos actually in the right amount. So it's a different kind of elementary particles. I mean, we mentioned in this class electron, proton, and neutron, but there is a huge class of other elementary particles that are also part of the mechanism that actually we mentioned positron, which is actually antiparticles of the electrons. So anyway, the point being in here is that now the Z has increased, the number of protons has increased in this case. So this moves one step to the left. For example, if I take nitrogen, and if it's capable of doing this kind of beta decay, so nitrogen becomes oxygen. So we move to the right. So this is moved to the right on the periodic table. This moves to the left in the periodic table, and so is this one also moves to the left for the alpha emission, always to the left for the alpha emission, okay? So the beta decay can do this. There is a third beta decay, the beta process that I didn't mention for this one, and actually through the something else called the electron capture. So what's going on in the electron capture? You have still a proton in this case, and it captures a normal electron, the regular electron. In this case, also it's going to become a neutron plus the emission of that neutrino also. It's going to come out of the process too. So in other words, this is also converting protons into no protons. Basically, in this case, if the electron comes too close from the nucleus, it could be captured by the proton. And if it does, then that proton becomes neutral because the charge in this case is you have positive charge and negative charge, they cancel, and they will give you a neutron, normal neutron. So in this case, this process also will move the particle to the left also in the periodic table. So if you have, for example, nitrogen, it could move to carbon. Or if you have oxygen, it could move to carbon. I'm just taking this as examples, okay? Please don't read this too much into their processes. I know, for example, there are some, usually they involve much heavier elements in these ones because these ones are a little bit more stable than the rest of the others. Now, this is basically what's going on. The last type of radioactivity, because the nucleus is too big, and for example, it's kind of sitting in an asymmetric fashion. So in this case, it's not completely spherical. So there is a rearrangement of the atoms, that's all. So this usually has a star next to it. So when you see an element with a star next to it, that means that it has an excess of energy because of the way that the protons and neutrons are rearranged themselves in here. So there is a bunch of protons on one side, for example, and a bunch of neutrons on the other. So they rearrange themselves to become more stable, okay? And there is a more uniform distribution of charges inside, protons and neutrons inside. And at the end of the day, they emit an energy, usually in the form of gamma radiation. So this is the gamma radiation. So in this case, what happened to the number of protons? They don't change. So just rearrange, that's all. So the number doesn't change. They just, the element, the same element. For example, if you take lead that is not stable, and it just becomes lead that is stable plus radiation in this case, okay? So this is the last one. So this one doesn't move the period. So lead stays lead. Whatever element that you start with stays the same element as you have before. So this is in a nutshell, basically what's going on inside the nucleus, trying to understand the processes of all of this and what's going on with the elements in the periodic table. This process is a random radioactivity is a probabilistic phenomenon, meaning a given element that is capable of doing either alpha radiation, beta radiation with all of its forms, and gamma radiation may or may not go radioactive anytime. So it may go now, you may wait for it for 3 seconds, you may wait for it for 3 days, you may wait for it for 3 weeks. When it's going to do that, it's not deterministic. So a single single nucleus, not nucleon, I don't mean proton, it's a nucleus in general, can go radioactive at any time. Okay, so when is it going to be? I don't know. Okay, so it's based on some sort of a probability, and the probability means that basically, let's say, for example, it's 50% chance that it's going to go radioactive in about 1 hour. But it could last for 3 hours, could last for 7 hours without going radioactive, or it could go radioactive in about 2 seconds. So that's basically what probability means. But if I take a large number of them, that is more deterministic because the law of the averages apply then, okay? So on a large number of nuclei is determined by their half-life. Half-life. What I mean by that is that every single element has its own half-life. So if you start with a mass or volume, it doesn't matter, of a given element, how long, that's the question, how long it takes for it to lose half of its mass. That's all. This is an exact science. So a single one is probabilistic. Bunch of them together, which is a huge number, usually of the order of Avogadro's number, which is 10 to the power 20 or something like 23 or something like that. The point being in here is that for a large number of them, they become more deterministic because the law of the averages will prevail. So if ultimately one of them doesn't, the other one does, and at the end of the day, they will come up with this deterministic behavior. So there are two types of terminology in here. So the parent is the starting element, and the daughter or daughters in general is the byproduct of this process. Okay, so that's basically how the terminology that is used. How long it takes for the parent to drop by a factor of half is the half-life. Okay, so this is basically in a nutshell part of the terminology. Some elements, they can take few seconds and they become radioactive. Some elements, few minutes, and they become radioactive. Others, they take thousands of years. For carbon-14, for example, to decay to carbon-12, it takes a long, long time, about thousands of years. This is what is used actually for carbon dating. Because you know how much carbon-14 is in the air on average because of the radiation that comes and hits the upper atmosphere and regenerates all the time the carbon-14 that is being consumed and actually transformed on its own, actually, to carbon-12 on average because of this process. But it's renewed at the same rate as it's being basically depleted from the atmosphere. So imagine with me, let's say, for example, I have 10 carbon-14 in the air right now. The process comes in here and adds 1. But one of this decays into normal carbon-12. So I lost 1 and I gained 1. So how much do I have? I still have 10. So that's what we know. Now comes a plant and takes carbon-14. That's what plants do. I mean, they take CO2, okay, including, it doesn't matter which C it does, it has in here. Carbon dioxide can be using carbon-12 or carbon-14. It's the same chemical elements in this case, which combines with oxygen to form carbon dioxide. This is the same chemistry, okay? So it takes carbon and basically goes through the processes and makes the different components of it. And now, if I look at this plant and find the ratio of carbon-14 to carbon-12, on a living plant, it's reflective of how much carbon-12 and carbon-14 are in the atmosphere, okay? Carbon-12 and carbon-14, they come with those proportions. A living plant will have this ratio because it's taking all the time carbon at that same rate and using it for its own growth. Now, when the plant dies, it's not taking any more carbon, meaning it's not taking any kind of carbon. So the carbon that it has in it is already done for. It doesn't have any more additional carbon. So the carbon-14 that it has starts to decay to carbon-12 on its own because of these processes that we were describing earlier. So in this case, I can come in here and find the ratio in this dead tree, for example, and determine that ratio. Of course, it's going to be a lot less than on a living plant. Then in this case, I can determine how old is, when did that plant die? When did it stop from consuming carbon in general? If an animal, for example, feeds on this plant, okay, its fruits or its leaves or whatever it is, then the same process. I can use the same process for that animal. If an animal feeds on an animal that eats plants, it's still also in the same way. So if that animal dies, also I can take that animal, find the ratio of carbon-14 into carbon-12 in it, and determine the age of that. That is the essence of carbon dating. Carbon dating is part of a process known as radiometric dating. And radiometric dating uses other elements, not necessarily carbon. For example, I know that uranium, for example, and magnesium and other elements, they can take into millions, possibly billions of years to decay into half. So their half-life is in the billions. Half-life in the billions. Obviously, this process is used for a lot longer dating, okay? For a lot longer than this one. And this is actually how we determine the age of the solar system and that of the Earth to be about 4.5 billion years old. Because we look at those meteorites that fall on the Earth, because we think that they're basically, they're not changed from the way that they formed. There are no other processes that happen to them. Take them, find the ratio of the isotope that is the parent to the daughter, or and see based on that how old it is compared to how much it should be. That is what we use for radio dating. Okay, anyway, I think this is the entire chapter. If you guys have any questions, please do not hesitate. I'm going to stop the recording right now, and I will see you today in the lab. Thank you.